Hello everyone! In this short video, I'm gonna introduce the idea of cooperative networks of deep neural networks. What's that? The idea of cooperative networks of deep neural networks is about building multiple neural networks that are able to learn how to cooperate and how to communicate with each other to achieve a common global goal. Well, in the last few years, deep learning has played a major role towards higher levels of artificial intelligence. In particular, in the last few years, deep learning has drawn inspiration from multiple sources, including how our brain works, including statistics, game theory, but it was also inspired by the theory of evolution, of living forms. And one crucial aspect in the theory of evolution is competition. So it's not that surprising that in the last few years, many deep learning systems were actually based on the principle of competition. One of very famous attempts are the generative adversarial networks, where we have a generator and a discriminator that are in a competition, where in particular here we have that the generator tries to fool the discriminator. The principle of competition has also been used in the context of deep reinforcement learning, in particular for automated game playing, like AlphaGo, for instance. Here we play many games and we actually learned a lot from the competition. Okay, but there is another element that play a major role in the evolution of living forms. And this element is cooperation, which is the topic of this work. In particular, in this paper, we asked ourselves, can we train multiple deep neural networks that automatically learn how to cooperate, how to communicate together to achieve a common global goal? In my opinion, cooperation can be a very, very important element to counteract uncertainty. And for this reason, exploiting the principle of cooperation may be very, very important to solve challenging problems. On the other hand, also our brain is composed of several areas that in such a way have to cooperate together in order to take good decisions in challenging contexts. And the challenging problem that we have tried to solve, to address in this work, is distant speech recognition, which is actually a very, very challenging problem, as we will see in the next slide. So, what is distant speech recognition? Distant speech recognition is also known as far-field speech recognition, and it's basically speech recognition in which the microphone is typically far away from the speaker. And you can use this modality in many practical applications, for instance, in automation, in smart TV, for meeting transcriptions, for healthcare, robotics, and many other applications. Despite the growing interest towards this modality, it's well known that distant speech recognition is a very, very challenging problem. Why? Basically because we have to deal with non-stationary noises and reverberation, which makes the speech signal significantly less intelligible and the speech recognition task very, very complex. This was actually the topic of my PhD thesis that is referenced below, and if you would like to know more information about this very interesting topic, you can take a read into my thesis. Okay, standard distance speech recognition systems are typically based on a pipeline like this, where there are several interconnected modules. We can have, for instance, a module for acoustic scene analysis that analyzes the acoustic scene, for instance, to detect areas where there is speech from areas where there isn't speech. Then we have a speech announcement module that has a primary goal of improving the quality of the speech signal before feeding the speech recognizer that finally retrieves the words uttered by the user. So even if this standard pipeline makes total sense, there are some prominent issues here. The one is the lack of matching. In fact, despite the growing interest towards end-to-end systems, typically all these submodules are designed independently, and there is thus typically a lack of matching between these architectures. But the other problem, which still holds even in end-to-end systems, is the lack of communication. Why? Because as you can see here, we have a unidirectional communication flux. For instance, we have that the speech announcement tries to help the speech recognizer, but the speech recognizer doesn't help in turn the speech announcement. So our idea is thus to break this flat pipeline and arrange all the basic components in a network where there is a full communication, a full cooperation between all the components. And that's the idea of networks, of deep neural networks, that here is applied to distance speech recognition, but it is actually a more general paradigm. In the network of deep neural networks, all the components are jointly trained, so there is a perfect matching between all the components. Moreover, there is a full communications between all the neural networks, and the networks learn automatically how to communicate and cooperate with each other. So there is a full communication in our networks of deep neural networks. Okay, this may sound like a good idea, but the big problem is, how can we train something like that? Our idea is to unfold the network of deep neural network in a way similar to that used for our recurrent neural networks. But instead of unfolding the architecture over the time axis, here we unfold the architecture over communication levels. For instance, we can start from a simple situation where all the networks are independent, and then we can progressively add communication levels where the cooperation, where the communication across the networks is progressively improved. And we can go ahead with this game until an arbitrary number of communication levels. So basically, at the end, we just have a kind of very big computational graph where everything is differentiable and where all the components can be jointly trained. So this is just a variation of the standard backpropagation algorithm that we have called backpropagation through network, to highlight that the gradient is backpropagated through a network of deep neural network. Okay, let me show you some results. In this study, we have evaluated our network of deep neural networks using several different speech datasets. For instance, we have started our experiments with a reverberated version of Timid, but we also have used the DIRA dataset that is a corpora recorded, a very realistic corpora actually recorded in a domestic environment where you have a lot of reverberation, but also a lot of conditions where you both have noise and stationary noises and reverberation. The first system, the first baseline that we have tried is a single neural network, in which we have basically in input some features like MFCC, and in the output we have context-dependent targets that are later decoded by an HMM decoder to estimate the sequence of words. Here, the results for TMIT are expressed in phoneme error rates, and for Wall Street Journal is word error rates, so the lower the better. Okay, we have also compared our network of deep neural network with a very competitive system that is based on the so-called joint training. Here we have basically a speech enhancement and a speech recognition systems that are jointly trained together. So the difference with our system is that here the communication flux is still unidirectional. But as you can see, you can clearly appreciate a performance improvement over a standard neural network baseline. Finally, we show some results obtained with our network of deep neural networks. As you can see here, we have our paradigm provides the best performance over all the tasks that we have tried in this study. And also it's very interesting to see that our network of deep neural networks is able to beat a very competitive baseline that relies on the popular joint training paradigm. So these results confirm that the cooperation helps to counteract noise. Okay, conclusion. In this presentation, we have seen that the proposed networks of deep neural networks can effectively counteract noise with cooperation, proving our initial idea that we can counteract uncertainty exploiting many neural networks that cooperate and communicate with each other. Of course, more research is needed here. In this presentation, we have discussed our implementation of this general paradigm, but maybe there are different ways to implement this idea, different algorithms, different architectures, and I think it's very important to research in the future in this direction. Let me say that in this talk we have applied this paradigm to distance speech recognition, but this is actually a general paradigm that can be applied to many fields. For instance, it can be used in a multimodal deep learning systems where a cooperation between different modalities can be exploited to improve the system performance. That's it. Thank you very much for your attention.